Hello and welcome back to geometry. Today in 19.3, we will be looking at the volumes of prisms, not prisons, and pyramids. So now we're going to, talk about how to find the volumes of three-dimensional figures. And to begin with, we'll just go ahead and look at these two then, okay? So first, what we'll do is we're going to have to kind of define what a volume is, even though, for the most part, we know what it is. So here is going to be postulate number 23, which is called the unit postulate. So this should look somewhat familiar because a while back we did the same thing, something called a unit postulate for when we find the area of something that is two-dimension. So in this case, it says that the volume of a rectangular parallelopid is the product of the altitude and the area of the base. So here is going to be a parallelopid, which is basically a fancy word for saying a rectangular box. Notice that we have the length, which we denote as L. We also have width, which we denote as W, and then we have the height, which we denote as H. So this postulate says that if I want to solve for the volume, the numerical volume of that product, the numerical value is supposed to be the product of all three of these things right here, because, technically, it's supposed to be the altitude and the area of the base. But the base right here, as you can see, is going to be the product of the length and the width. So length and the width, that right there is going to be our base, and multiply by the height over here, which we denote as h. So multiply the three dimensions together, that will get us our volume. Now, to make things a little bit easier, let's look at a consideration. Let's consider the situation of a cube. Let's consider where the length is equal to the width is equal to the height. And for the purpose of making it simple, let's just say that they're all equal to 1. So if they're all equal to 1, then in this case, you can see that the volume is then equal to 1 because it's 1 times 1 times 1. Now, we're going to go ahead and use that to figure out how to find the volume of a pyramid then. So this right here is kind of an illustration, not necessarily a proof of how this actually works out. And what I have is basically that cube that I was just talking about. So we have a length of 1 over here, we have a length of 1 over here, we have a length of 1 over here. So you can see that the total volume, as we said, is equal to 1. What I would like to do is utilize this cube or use this cube to figure out what is the volume of a pyramid. Now, the pyramid that we're looking at is going to be the specific shape where the base is going to be a square. So that means that we have kind of like a base pyramid then right here. And then that is going to have the, and then you have a vertex, which is going to be somewhere vertical. So something like this then, okay? Note that it could be the case where the pyramid could have the vertex somewhere right above one of the corners then. So that means it could actually look something like this. And it turns out that according to something called the Cavaliers Principle, that these two shapes have exactly the same volume. Okay, let me read it again. These two shapes right here, so long as the base is the same and the height is the same right here, then that means the volume of one is equal to the volume of the other. A little hard to believe, but if you can kind of see the illustration, here's how it works. The base over here, let's say that it's a square, right? Which is the same as the base that is going to be a square. Now, if I go up to a certain cross section, then you can see that that's going to be a square also. Now, on the other triangle or on the other pyramid, that also could be potentially a square as well, because all you're doing is you're just kind of like shifting it over. Imagine it this way. Cavaliers Principle works because let's say that we have a textbook, which we lay flat on the surface and it looks something like this. So you can see that it has a certain volume. Now, Cavaliers Principle says, hey, let's go ahead and take that textbook and we're going to go ahead and kind of push it to the side by about 45 degrees and so. So then that way you have kind of like like that parallelepiped, which is going to be kind of like, lopsided. The shape of it is a little bit different, but the volume is going to stay the same thing because all the cross sections are exactly identical. So that's exactly what's happening over here. When I draw that cross section for the other one, it's going to stay the same. And even if it's not the same, it turns out that even if the cross section's area is not the same, it turns out that so long as all of those pieces have the same cross section area, then that means the volume is going to end up to be the same. But anyhow, going back to our question over here, right, or how this actually works out is, I want to find the volume of the pyramid according to this cube over here. Now, notice that I have 3 cubes over here, and according to Cavaliers Principle, they are all going to be the same volume. Because if you notice, they have the square base, which is what we're referring to, and the height of each one of these is actually going to be the edge of one of these sides right here. So here you can see that that height is going to be, the height is actually over here, sorry about that, is going to be the same as the height that's over here. For the red one, the height is going to be this part over here. And then for the black one, the height is going to be the back side that's over here. But here's the amazing thing. If you notice that I have these 3 triangles, it is possible to take all 3 of them and put them all inside the square. The way that I'm actually, it is possible to take all of these triangles, the pyramids, and put them all inside a cube. And here is how I can do that then. Notice here we have the for the green pyramid, the face is going to be that square, which is located right here. So I'm going to go ahead and put it in so you can see how that works out. Okay, so there's one part. And then now for the red pyramid, I am going to align it so that it's inside the cube, but then it matches up with the square that's on the bottom, and there's the second part. But before I put that in, let's go ahead and put in the black part so it's a little bit easier to see. So the black pyramid, you can see how it aligns with the bottom square, and there it is, that wedges into the bottom right there. And finally, for the red, I'm going to go ahead and put it right there, okay? So all of these 3 pyramids, they're all going to converge at that point of vertex, which is located over here then as a result. So the question is, well, what does that mean? Like, how does that help us out? Well, if the 3 pyramids are all congruent to each other because of Cavaliers' Principle, then that means that they all have the same volume. And if they all have the same volume and they all fit into this cube of 1, then I'd like to think that the volume of one of those pyramids is going to be equal to 1/3 of the size of the cube. So it's going to be 1/3 of the cube. So 1/3 of the volume of the cube then. So hence, finally, the formula in this case, it's going to be equal to 1/3 multiplied by the base multiplied by the height then. Okay, so that right there is how we go ahead and find out what is the volume of the pyramid. So in our case, here, remember the base is supposed to be a square in this case, right? So the base is going to be the area, which is going to be 1 times 1. And then the height over here, we said that that's equal to 1. So the volume of this cube right here is supposed to be equal to 1/3 multiplied by 1 times 1 times 1. And that's how we can find the volume then. Okay. All right. So this Cavaliers Principle right here is actually very unique and is very it's something that we can actually utilize to figure out how to find the volumes of other three-dimensional things that are a little bit more complex. So say, for example, maybe if we have, like, say, a cone where all the cross sections are going to be circles. It turns out that the Cavaliers Principle actually applies to this too. So what that means is if I have, like, say, a cone right here, and then I also have a pyramid right here, where the areas of each cross sections are congruent to each other. So that is to say that assuming that this square, the area of it, is equal to the area of this circle over here. Then if we go to next tier up, if I say that the area of this square is then going to be congruent to the area of this circle. And then we keep going up and up and up and up and up and so on and so on and so on. And it's going to be the case where they're going to be consistent to each other, where the height of one is going to be equal to each other. So assuming all those cross sections area are going to be the same and the height's going to be the same, then I'm going to say that the volume of the pyramid is going to be equal to the volume of this cone, according to Cavaliers' Principle. Okay. All right, so now let's go ahead and take a look at how we can utilize just give an example of how to use the volume of a cone or volume of a pyramid in this case, okay? So let's look at an example in this one. A square-based pyramid have an edge length of 6 and 4 congruent equilateral triangles as its lateral face. Solve for its altitude, the volume, and the total surface area. Okay, so let's first start by drawing out what the picture looks like so we can figure out how to actually solve for this. So a square-based pyramid, so that means that the base is going to be square. So that means that we can draw that out just to begin with. The length of the edge is going to be equal to 6. So that means that this is 6, and this is 6, and so on and so on. Now, I'm going to have to draw this using 3D, so bear with me over here. We are going to have 4 congruent equilateral triangles as its lateral surface. The lateral surface is defined as all the surfaces combined that are not the bases then. Okay, so let me repeat again. The lateral surface is basically the face of all the surfaces with the exception of the base. Okay, so what that means is when I draw that pyramid, okay, we're going to draw the pyramid up here, right near, right basically the center of the square right there. From there, we have 4 sides right here. We have 4 edges. So here's one, here's another, here's a third, and then here's a fourth. So you can see how for the pyramids, you have 4 sides that are going to be equilateral triangles, just as it says in the problem, where the length of it is equal to 6. So those 4 sides, those are my lateral surfaces. Okay, so right there, the red right there, that's my lateral surface. Whereas this right here, the blue, that is going to be the base. So kind of like some new terminologies. All right, so there you go. Now I want to find out what is the altitude to this pyramid. I want to solve for the volume of this pyramid and also the total surface area then. Okay, so solving for the altitude, well, let's go ahead and draw the altitude so you can see how we can solve for that. Now remember, the vertex of this pyramid is going to be directly above the center of the square. So what that means is what we can do is draw the diagonal through the square, and from there you can see that we have also an isosceles triangle where this guy right here is going to be perpendicular, and that right there is going to be the height that we need. Okay, so that's going to be their altitude. Now, taking that triangle and pulling it out, just so you can see how that's solved for, this is what it looks like then. So the side, let's see, is supposed to be equal to 6 over here. The side is equal to 6 over here. The height right here is right down the middle, which is going to be h, and there's a right angle right there. The length of the diagonal, since it's a square, then that means, according to my proportionality, this is going to be equal to 6 root 2. All right. So hopefully everything matches up so far. In terms of what type of triangle it is, we just know it's an isosceles. We don't know if it's an isosceles right triangle, so we can't use those scenarios in this case. But anyhow, knowing that that's going to be equal to 6 root 2, the diagonal, then that means that this guy right here, that is going to be equal to half of it, which is going to be 3 root 2. And that is going to allow us to solve for the h, the height, using the Pythagorean theorem. So 6 squared, which is going to be the hypotenuse, is equal to h squared plus 3 times root 2 quantity squared. So 36 is equal to h squared plus 9 times 2, which is going to be equal to 18. So that means h squared is equal to 18. So that means that h is equal to the square root of 18, which actually comes out to be 3 root 2. So hey, look at that. That means we have an isosceles right triangle, which is, good to work with. All right, so now that we have the height, then let's go ahead and solve for the rest of it. So that right there is going to be my altitude. Next, we're going to go ahead and solve for the volume. The volume is supposed to be equal to, according to what we just saw for, 1/3 times the base multiplied by the height. Well, we have all those numbers right here, right? We have 1/3 as is. The base is a square, so that's going to be 6 times 6. And then times the height, which we just found out, is going to be 3 root 2. So multiply all that out. So your answer is going to be equal to 36 root 2 then. And I guess if you want, you can say unit square or something, just for the unit then. Finally, let's go ahead and solve for the total surface area. Now, this right here, keep in mind that that's going to be 3-dimensional. This right here, the altitude, that is going to be 1-dimensional. And then what we're solving for the surface area, that's going to be 2-dimensional, okay? So that will give you an idea as to like what type of units you should be yielding. Okay, for the surface area, then that means I need to solve for the area of each of the triangle and then add it with, well, I think that's it because I don't include the square parts. So the lateral surface area, I'm sorry, I'm asking for the total surface area, not the lateral surface area. So we do actually add the square, okay? So remember, lateral surface, that means we're just adding everything that is not the base in terms of the area, and whereas the total surface area, we do include the base. Okay, so the total is, surface area is equal to, it looks like we have those 4 triangles, right? 4 equilateral triangles, plus the 1 square that's on the bottom. So the area of an equilateral triangle is supposed to be s squared root 3 over 4. That's from a while back. So that is going to be s squared, so s being 6 in this case. So 36 times root 3 over 4. And I'm going to go ahead and put it on the side. So area of an equilateral triangle is s squared root 3 over 4. Then we are going to add that with the area of the square that's on the bottom. So that looks like it's going to be 6 times 6. So cancel out the 4. So that means we have 36 root 3. And then we have plus 36. And right there, that is going to be my total surface area. All right. Well, thank you so much for watching. And I will see you guys next time then. Take care. Bye-bye.